introduce your. Hello everyone. Today is the last lecture and also first lecture of İzzet Coşkun. He will give a lecture about birational geometry of Hilbert scheme of points on surface. And we can start now.
Well, thank you very much. Thanks for the invitation to give these lectures. So, you know, I see that there is a large range of people ranging from at least graduate students to faculty members. So, you know, I'm going to pitch these lectures to somebody who has just maybe read Hartshorne. So, you know, if there are things that I say that don't make sense, feel free to interrupt me, okay? So the basic problem that I'm interested in these lectures is the following. So X will be a smooth projective variety. And the configuration space of X, so maybe sometimes written like the configuration space of X, is simply the set of n unordered points on X. So it's the set of, you know, sets of points P1, Pn, and these are, you know, such that these Pi are distinct points in X, okay? And this set is this configuration space is very important, and it comes up in lots of different things in mathematics. Like for instance, you know, if you want to study secants to a manifold, or if you want to study braid groups, things like this, this space is always at the center of these kinds of questions. But the basic problem with this is that it's not compact, right? Simply because what can happen is that if you have a manifold and if you have two distinct points, for instance, what can happen is that the point can approach the other one and then they can collide, right? So the basic question that arises is that how do you compactify the configuration space? And there are various ways of doing this. So there is one very naive way of compactifying the configuration space, and that's what you can do is you just let the points collide. So that's called the symmetric product, and this is what you can do. You can take X, take n copies of X, right? So you take n copies of X, right? And now the symmetric group on n letters acts on the space. So the symmetric group on n letter acts on this. And how does it act? It just shuffles the points. So if you have P1, P2, P3 up to Pn, then you can move them around. And then what you do is you form the symmetric product. This is called the symmetric product. And what it is simply you take this xn and quotient out by this action of the symmetric group, okay? And this is now a compact space, and it contains the configuration space as an open set. So it's a sensible compactification. And if the dimension of X is 1, so say that the dimension of X is 1, and here, of course, I should be clear that we are working over the complex numbers. And when I say the dimension of X is 1, that means it's a complex curve or a Riemann surface, okay? Then this symmetric product is a beautiful space. So this is a beautiful space. And we understand its structure relatively well, at least if n is large enough. So you see, if you have a complex curve, then, you know, topologically, it's a Riemann surface, so it has a genus, right? G is the genus. So it's the number of holes in the topological surface. And if n is large compared to G, then, you know, it has a very nice structure. So say that n is I guess I need it to be bigger than or equal to 2g minus 1, then we can completely understand the structure of this. I mean, we can understand it even when n is smaller, but then it's a little bit more complicated. And the way you can think about this is that the symmetric product admits a map to the Picard variety. So now what is the Picard variety? The Picard variety is this isomorphism is the variety that parameterizes isomorphism classes of line bundles of degree n. So this is actually a complex torus with, this is a complex torus with dimension g. So complex torus of dimension g. And you see there's a very nice map if you have a set of points p1 dot dot dot pn, possibly with repetitions. What you do is you send that to the line bundle that you get by looking at the sum of these pi's. And you see what this is that the fibers of this map, so this map is surjective as soon as you know, n is sufficiently large, and sufficiently large means something like g, yeah? But when n is at least 2g minus 1, the fibers of these things are all projective spaces with the same dimension. So what this is that this is p n minus g bundle over a complex torus. So in particular, you see, you can understand the geometry, the topology, a lot of the things about the space very nicely, and you have a very concrete compactification of the configuration space that we started with, okay? So that's the story in dimension 1, if the dimension of x is 1. So the next question happens, what happens if the dimension of x is bigger than or equal to 2? Now, the problem with the symmetric product, the problem we have now, this is singular. You know, usually when we work with spaces, the kinds of things that we want to do is, you know, we want a compact space and we want it to be a manifold, right? Singularities and non-compactness give us all sorts of headaches. So now, how do you fix this? So Grothendieck had a beautiful idea of reinterpreting the curve case. So maybe let me do an explicit example. Let's do an example. So let's look at the case when x is p1. So that's the Riemann sphere, or, you know, complex projective line. So you see, let me draw it as a sphere. And now you see, we talked about like points on this. So if I have n points on this, right? Say that you have x1, y1, dot, dot, dot, xn, yn, right? Instead of thinking about the n points, right? I can think about the polynomials that vanish on those. Polynomials that vanish on these points. So you can write it like this. So, you know, it's generated by this polynomial. So I can do x times yi minus y times xi. So I can take this product. And this polynomial, you know, any polynomial vanishing on these points is divisible by this polynomial. And this polynomial is uniquely determined up to a scalar, right? So that way you see that instead of thinking about the points, right, on P1, n points in P1, I can just think of this polynomial. And of course, the points are just the roots of the polynomial. Okay, so instead of parameterizing the n points, you know, by what we were saying, the symmetric n product, we can parameterize this by the coefficients of the polynomial, right? So this is really what this is saying, is that this n symmetric product of P1 is nothing other than projective n space, given by the coefficients of this polynomial of degree n up to scaling, okay? But now you can take this, you can take this further, and instead of thinking about, you know, points on the space X, you can think of the ideals of polynomials that vanish on those points. So Grothendieck's idea, instead of parameterizing points, think parameterize ideals. Ideals that vanish on the points. And you can do this much more generally, not just for points, but you know, for any kind of scheme. So maybe let me introduce this a tiny bit. So you see, if I have a projective scheme, if you have X in Pn, right, then associated to this X, you have a Hilbert function. Now, what's the Hilbert function? So age of n, or age of m, say, right, is the polynomials, is the dimension of the vector space of polynomials of degree m modulo those polynomials of degree m that vanish, modulo those polynomials of degree m that vanish. These, I should say, homogeneous polynomials. Homogeneous polynomials of degree m modulo those that vanish on X. Okay, so this gives you a function for every positive integer. You look at linear polynomials modulo those that vanish on X, quadratic polynomials modulo those that vanish on X, and it's a theorem that goes back to Hilbert. Is that, I mean, you know, there, if you've taken Hartshorne, you can think of this as age naught of OX of M, right? That's what this is, right? But you know, it's a theorem going back to Hilbert that this becomes a polynomial. Initially, this might not be a polynomial, but as M is becomes sufficiently large, this function age m becomes the same as a polynomial, and this is called the Hilbert polynomial. Okay, so maybe let's do a quick example just to see, right? So if I had the plane, if I had P2, and say that I had 3 points, right? Here, let me take the points 1, 0, 0, 0, 1, 0, 0, 0, 1. XZ, YZ, right? So now if you ask, what are the polynomials at the, so you know, here we're asking homogeneous, so let's compute this function. So let's find H1, H2, H3, and so on and so forth, right? What are linear polynomials that vanish on these 3 points? Of course, these don't lie on the line, so there are no linear polynomials that vanish on these. So the polynomials at degree 1 are given by x, y, z, so that's 3-dimensional vector space. Quadratic polynomials are given by x squared, y squared, z squared, x, y, x, z, y, z. X, y, x, z, and y, z vanish on these, so you see there's a 3-dimensional space of such polynomials. And then, you know, you can keep doing this. If I look at cubics, right? If I look at cubics, you see that x cube, y cube, and z cube don't vanish on these 3 points. And any other cubic monomial vanishes because it's either divisible by xy or xz or yz. So that you see that's 3, and you see that this way Hm is always 3. So in this case, you see that this is the constant polynomial 3, like Hm is equal to Pm is equal to 3. But you see, like this Hilbert function is a little bit sensitive to where the points are. So let me do another example for you so that you see. So let's take 3 points now that are collinear, right? So let's just say that we took 1, 0, 0, 0, 1, 0, and maybe 1, 1, 0, right? If I check this, if I take this set of points, then you see that the ideal now is generated by z, right? And xy, x minus y, right? So the ideal looks a little bit different, right? And now if you wanted to do this, like you see H1 now is different because, you know, if I take the polynomials of degree 1, x, y, and z spanned by x, y, and z, modulo those that vanish on the set, z is 1, z is such a polynomial, so you see that this is now 2-dimensional. But starting with H2 onwards, then this thing becomes 3 again. So to see that the quadratic polynomials, you see I have x square, y square, xy, xz, yz, z square, xz, yz, and z square vanish on your scheme because already z vanishes, so that you see this 3-dimensional span by x squared, xy, and y squared, and so on and so forth. And then you can work this out that here you see that this function is not exactly a polynomial, right? H1 is 2, but afterwards it becomes a polynomial, okay? All right, so this is a quick review of the Hilbert function and the Hilbert polynomial, right? And Grothendieck's idea was, so Grothendieck says that what we should do is we should parameterize all ideals with a fixed Hilbert polynomial. And Grothendieck's big theorem is that there exists actually a projective scheme called the Hilbert scheme that does parameterize such things. So Grothendieck's theorem says that there exists a projective scheme which is called the Hilbert scheme, which parameterizes you know, subschemes of our projective subscheme Z of our projective scheme X with a fixed Hilbert polynomial, So if we wanted to parameterize, so let's go back to what we were talking about. So remember, this started by thinking about, let me go all the way back to the beginning. We started by thinking about the configuration space, which was configurations of points on X, right? And the idea was, you know, the problem was that the symmetric product was, okay, a compactification, and in the case of curves was a nice smooth compactification, but in higher dimensions it was singular. So instead we were going to parameterize polynomials that vanished on our finite set of points, right? So what we want to do in that case is that we want to parameterize, so for our case, for our purposes, we would like to parameterize, we would like to look at, you know, the Hilbert scheme of X, right, corresponding to a constant polynomial n. So the constant polynomial n. And so this is, for short, that's usually written like this, the Hilbert scheme of n points. Any questions so far? Well, I see there are some chats. Okay.
There is no question in chat.
Okay, so if you have any questions, you know, just unmute yourself and ask me, okay? All right. So I'm being a little bit sloppy in the way that I'm describing this theorem. This theorem is really much nicer than I'm making it sound, right? in fact, you know, so this Hilbert scheme is actually a fine moduli space for something called a Hilbert functor, but I'm not going to worry too much about those kinds of things. And I urge you to look at various places. You know, for instance, you could look at a book by Harrison Morrison on moduli spaces. You know, the beginning of that book has a discussion of Hilbert schemes. There are, Mumford has a book called Curves on Surfaces, I think, that has a construction of the Hilbert scheme and so on and so forth. There you can find many references that construct the Hilbert scheme and discuss the properties. What I want to do is sort of, you know, play just with the Hilbert scheme of points, okay? So let me just say, you know, the way I presented this is that we wanted to find a nice smooth compactification to configuration space. The problem is that if the dimension of X is bigger than or equal to 3, the Hilbert scheme is not really any better. In fact, in many ways is worse, right? Then Xn is not that well behaved. Okay, so let me give you a quick example due to Yerbino. So this is like, you know, if you take, so this is going to show that if the dimension is at least 3, then the Hilbert scheme is not irreducible. It has many components and it has different dimensions, okay? So let's do the following. So what I'll do is I'll work on P3 or C3, doesn't matter. Let's work on C3. So let me, I think I want to look at Hilb 96 of C3, all right? Let's just understand. All right, let's just understand what Hilb 96 of C3 looks like, or not understand, but just see the kinds of things that can go. See the kinds of things that can go wrong. Here is what we are going to do. So you know, here, like, let's take the origin, right? So before maybe we start with this, let's figure out what's the configuration of C3 look like. So now you have n points in C3, right? So the dimension of the configuration space, I should have said this. So the dimension of the configuration space, right, is n times the dimension of X, right? Because, you know, you are just choosing, you know, as an open set, it has an open set of the symmetric product of X and symmetric product of X, and the dimension of that is n times the dimension of X, right? So in this case, we expect, right, the dimension of the Hilbert scheme to be 3 times 96, and that should be 288. Right? So I expect the dimension of the Hilbert scheme to be 288, right? All right, but now let's see. So let me give you some ideals with a given Hilbert polynomial. So let's take the origin, as I said. Let me write it again. Let's take the origin. So we have the maximal ideal at the origin, and that's generated by x, y, z, okay? So now let me take the 8th power of the maximal ideal. So if you want, that's generated by, you know, things like x to the 8th, y to the 8th, z to the 8th, you know, more generally x to the I, y to the j, z to the 8th minus I minus j, okay? All right, now let me also take a 24-dimensional subspace of homogeneous polynomials of degree 7. Okay? Again, I don't care what the subspace is. Take any subspace, the homogeneous polynomials at degree 7, like you could take x to the 7y to the 7z to the 7, and then, you know, put another 21 monomials in there, and then look at the subspace span by that. That would be an example, okay? So now as my ideal, right, let's just take, let's call the subspace V, right? Take this V plus take this m to the 8, and let's look at the ideal generated by this. Notice that I only vanishes at the origin. Okay, I vanishes at the origin. Okay, but now let's see, but so, you know, so, but let's see what kind of, so, you know, this is a case where all the 96 points, so to speak, are concentrated at the origin, but let's look at what the Hilbert polynomial is. So, you know, the way to compute the Hilbert polynomial, so you can compute the Hilbert polynomial, you look at, I guess we are working over the complex numbers, so you look at Cxyz modulo I. This is a finite dimensional vector space, so you compute the dimension of this vector space, okay? But you see, this is, let's compute it. So what did I do? I killed all polynomials of degree 8 or more, right? And then I killed the subspace of the polynomials of degree 7. So I have the constants left. So there is one constant, one dimensional vector space with constants. There are 3 linear forms. So these are constants. These are the linear forms. Then I have quadratic forms. There are 6 quadratic polynomials, right? X squared, xy, y squared, xz, y, z squared. There are 10 cubic forms, 15 quartic forms, 21, where is that? 2, 3, 4, 5, 28, 20, so this is degree 3, degree 4, degree 5, degree 6. And then I have degree 7. How many degree 7 forms do you have? You have 36 degree 7 forms, except that we killed 24 of them. So there are 12 remaining degree 7 forms. These are the remaining degree 7 forms. So you see that this dimension, hopefully if we did it right, was going to be 96. So this is 10, this is 20, this is 36, so it's 56, and this guy is another 40, so that I get 96. So you see that an ideal like this also lies in C3 of 96. Okay. All right. Now here is the surprising part. Let's count how many such ideals there are, right? What did this ideal depend on? It depended on 2 things. I needed, first I had my C3, and I needed to choose a point on C3, right? So there's a 3-dimensional choice for the point. This is choosing, right? And then the other thing that it depends on is this 24-dimensional vector space, right? The, like, degree 7 forms is a 36-dimensional vector space. So inside the 36-dimensional vector space, I need to choose a 24-dimensional vector space. So that's given by the Grassmannian. So you have the Grassmannian of 24-dimensional vector spaces inside a 36-dimensional vector space. And then the dimension of this is 24 times 12. This 12 is 36 minus 24 is 288. So you see that the locus of such ideals is already 291. Now, why is that surprising? I mean, this is surprising because we were expecting the dimension of this Hilbert scheme to be 288. In fact, the configuration space, the component that contains the configuration space, consists of this, is a 288 dimensional space, But here we have another locus that's 291 dimensional. What the conclusion that we get from this, if you want, conclusion, is that the Hilbert scheme, the C396, is not irreducible, is reducible. It has at least two components. I mean, what's worse is that, you know, what we wanted to do is we wanted to find a compactification of the configuration space. So the picture we had in mind is that here is my configuration, like here's my X, and here were some points moving around. You know, I just wanted these points to collide and put a limit to that, right? But what this is saying is that if you look at the Hilbert scheme, if you take a general point in this component, then you can't, it's not a limit of distinct points. So a general such ideal is not a limit of ideals with distinct points. All right, so this is to make a long story short. So let's go back to what we were doing. We started out by saying that we wanted to compactify the configuration space. You know, the symmetric product was one compactification. In the case of curves, it was beautiful. In the case of surfaces and higher, it was singular. Dan Grothendieck had the idea that maybe we should instead look and compactify the space of ideals. I should have said that the Hilbert scheme in the case of curves agrees with the symmetric product, right? But we see that in higher dimension, if the dimension is at least 3, then actually the Hilbert scheme is not just the compactification in the usual sense of the word, okay? So that's why we just look at the case, the dimension of X equals 2. So this is to say that's why we are talking about the case of surfaces. And here a miracle happens. I'll just say it like this, miracle happens. And here is the theorem due to Fogarty. So X here is a smooth projective surface. Okay, irreducible. Then the Hilbert scheme of n points is smooth, irreducible, irreducible of dimension 2n. Okay, so in other words, you really get what you expect, that you get a smooth space, it's an irreducible space, and its dimension is 2n like you expect. Okay, so the dimension 2 case is special, and you know it differs from the what did I do? And it differs from the so maybe what I'll do is I'll maybe briefly sketch how you think about this. So let's briefly sketch. So sketch. The thing that you should understand is that, you know, when we talked about the Hilbert, when I told you the theorem about the Hilbert scheme, I was being very sloppy, and I briefly mentioned that in fact the Hilbert scheme represented the Hilbert functor and that it was a fine moduli space. One consequence of this is that we know the tangent space to the Hilbert scheme at any point, the tangent space to the Hilbert scheme. And this is not just, you know, for the Hilbert scheme of points, but more generally, we understand the tangent space of the Hilbert scheme relatively well. And then, you know, if you have the tangent space to a scheme Z to the Hilb, you know, P of X, this thing is basically Hom I to O mod I. Okay. All right. I'm not going to tell you how you get this, but that's not that difficult if you set up the theory right. You know, if you know that, so how do we think about the Zariski? So maybe let me explain a tiny bit. How do we think about the Zariski tangent space to a scheme? So the Zariski tangent space to a scheme is given by the homomorphisms from spec, I guess, let me do it, C epsilon mod epsilon square, right? To your, so this is very generally, if I had some X and I wanted to understand the Zariski tangent space at the point X, you look at spec C epsilon mod epsilon square and you look at homomorphisms from that to X such that you know, the way to think about spec C epsilon mod epsilon square is that you can think of it as a point together with the tangent vector, right? So you look at those homomorphisms such that they take the point to the point X, right? So this is your point X and X, and you want to understand the tangent space X to X, right? So you look at the homomorphisms from spec C epsilon mod epsilon square to X that map the point to X, and then you look at all such homomorphisms, and as you do that, what you get is the Zariski tangent space, right? So now you see, the key point about the Hilbert scheme being a fine moduli space is that there is a one-to-one correspondence between families, families parameterized by a base and morphisms from that base to the Hilbert scheme. So that's the key property. And then, you know, you can, so in other words, if you wanted to understand homomorphisms from spec C epsilon mod epsilon squared to the Hilbert scheme, that would just mean that you would have to find families, flat families over spec C epsilon over epsilon squared with the fixed Hilbert polynomial, where over the central fiber, you have the point that you want to map to in the Hilbert scheme. Now, if you analyze what that means and unpack that, you can see that what that means is that you can compute this Hilbert scheme, the tangent space of the Hilbert scheme. Now, in the case of surfaces, right? So now what we would want to do is we want to compute Hom I to O mod I, right? Well, if you want to find this, the key point that turns out to be is that no matter what the I is, this dimension is always 2n, okay? So, all right, so this is a relatively, this is not such a hard calculation, so let's maybe just do it. So you have the standard exact sequence, the ideal sits in the structure sheaf, and then what you get is OZ, right? Now here, of course, we're back to, when I write this now, we are back to this is the ideal sheaf of n points with Hilbert polynomial of n points, right? Or I don't mean this, but what I mean is that the ideal sheaf with Hilbert polynomial equal to n, okay? So now what we get here is that we have this, and what we want to do, so what we apply is we apply Hom blank OZ. You see, if you do that, then you have a long exact sequence associated to this. So you get 0 goes to Hom OZ, OZ, goes to Hom OOZ, goes to the thing we want to understand. Let me see whether I can fit it here. Hom, sorry, this, I'm not so used to writing on this iPad thing yet. So, okay. So then here you have X1, OZ, OZ, X1, OOZ, X1, IOZ. Then we have the X2s. X2 IOZ. And then, of course, because we are on a surface, then this goes to 0. There is no higher x, right? Now, you see, we understand these really well. So x1 IOZ and x2 IOZ, this is just h1 of OZ, and this is h2 of OZ. But this is a 0-dimensional scheme, so it doesn't have any higher cohomology, so that you see that these are 0, right? This is because by the Grothendieck vanishing theorem, right? If you have the cohomology of a scheme like vanishes past this dimension, right? So in particular, you get that this is 0, this is an isomorphism, right? The other thing that we know is that this is an isomorphism and they are both CN, right? This is the fact that we have the Hilbert scheme of n points, or this, if you look at the, dimension of the O mod I is an n-dimensional vector space. So this is an isomorphism. So if we want to understand this, we really want to understand this, okay? But what's good is that we also understand this. This we understand by Serre duality. We have x2 OZ OZ is the same as HOM OZ OZ, if you want, omega x dual. But this is 0-dimensional, so this is the same as HOM OZ OZ dual, so we know that this is also CN. Okay? All right, but we still need to understand this x1 OZ OZ, and then the final thing that you note is that the Euler characteristic of OZ OZ, which is written as -1 to the I xi OZ OZ, this is 0. Okay, again, this is not hard. You can use this, the definition, the definition of x to compute. You can give a projective resolution of OZ and actually calculate this. This is 0, right? But so then if it's going to be 0, here I have Cn, so that's n-dimensional. Here I have Cn, that's n-dimensional. So this plus this minus this has to be 0, so that you learn that this has to be C2n. So that you see that this tangent space that we wanted to calculate was always 2n-dimensional, okay? Anyway, that's a relatively fast calculation, that uses hopefully stuff you're familiar with from Hartshorne, but if not, you can find this kind of calculation in various places. But the key point here is that what the conclusion, so let me summarize the conclusion. So the conclusion is that the tangent space to xn, here let me remind you, this is a smooth projective surface, always has dimension 2n. Okay, so now here is the picture. So you have sort of the closure of the configuration space. This is a 2n-dimensional thing, right? So it suffices to conclude that this scheme is smooth and irreducible, suffices to say that it's connected. So enough to say because if it's connected, right, and then it means that, so you have this component of dimension 2n, so because the Zariski tangent space has the correct dimension at each point, so that component is smooth everywhere, but it's all, if it's connected, then it means that there can't be any other thing, right? Because if there was something else, then, since it's connected, it would have to intersect there, and here, like, the tangent space could not be 2n dimensional because you're singular, okay? So that means that if it's connected, then that's it. You have just the closure of the configuration space and there are no other components. But now how do you check that something is connected? Well, you do induction on n. So this is relatively easy. This you can check by induction on n. Well, I assume that the surface itself was irreducible, so it's certainly connected, right? So then what you do is you look at xn minus 1 cross xn, right? And here you look at the pairs where you have a w and a z such that w is contained in z, okay? So what you do is, you know, on the one hand, this maps to xn minus 1. On the other hand, it maps to xn, right? And the key point here is that, you know, if I know that this is connected, then it follows that this is connected, right? By induction, I know that this guy is connected, and then it's a matter of understanding the fibers and showing that the fibers are connected, which is not a hard thing to do, okay? So you know, you do induction on n to show that this xn is connected. So the final conclusion is that this xn is smooth irreducible. Dimension equal to 2n. Okay? In other words, so that's, let's go back to the statement of Fogarty's theorem. So if X was a smooth projective irreducible surface, then what we conclude is that the Hilbert scheme of n points itself is smooth irreducible of dimension 2n. In other words, it's a beautiful compactification of the configuration space. Okay? So I didn't do this, but maybe I should do it a little bit. So, so let's think a little bit. There is still a morphism. So there is a morphism from the Hilbert scheme to the symmetric product. So this is the Hilbert scheme. This is the symmetric, maybe I should write this because you can't see what I'm pointing at. So this is the Hilbert scheme. This is the symmetric product, right? There is a morphism, it's called, it has a name, it's called the Hilbert-Schemes morphism. Okay, and what does it do? Set theoretically, this morphism is easy to understand. You need to work a little bit to say that it's a morphism, but what it does is the following thing. Suppose that you have a scheme of length n, say I have a z, right? So then what you do is you send this thing to basically its support counted with multiplicity. So basically you do the length at pi of z times pi, okay? In other words, what this is that, you know, let's just see, here is your x. If you had n distinct points, you just send it to the corresponding point in the symmetric product, right? But, you know, if you had, for instance, a multiple point, maybe you have a double point, maybe you have a triple point, and maybe you have two simple points. So let's call this P1, let's call this P2, P3, P4. So I said this was a double point, this was a triple point. And what you do is you send this thing to 2P1 plus 3P2 plus P3, P4, okay? In other words, what you do is you take the points, you send them to their support counted with multiplicity. And, you know, you need to show that this is really a morphism, but it really is, okay? And so you get a nice morphism. And this, in fact, is a resolution of singularities. So maybe let me say it here. So this is a resolution of singularities. And it has very nice properties. So it's what's called a crescent resolution. Crescent resolution. What that means is that usually when you have a birational map like this, you have a Jacobian that sort of corrects for, you know, you have the Jacobian determinant that corrects for what the canonical sheaf is. To say that it's a crescent resolution is that there are no corrections. So if you take the canonical on X, on the symmetric product and pull it back, you get the canonical on the Hilbert scheme, okay? So that's what that means. So it's actually a very nice, but let's maybe understand things a tiny bit better. Sorry, I'm keeping sliding this. I don't know how to keep too many things on the board at once, but so let's understand, like maybe I should have done this a little bit earlier. Let's understand the difference. So the difference between the Hilbert schema and the symmetric product a little bit, okay? So suppose that I have 2 points, right? If I had 2 points, of course, if you have 2 distinct points, right? Then, so this is when we have 2 points. Let's just try that first, right? If I have 2 distinct points, then, you know, there is no difference between the symmetric product and the Hilbert scheme, right? You know, it's the 2 points you can determine this ideal. But you see now what happens if the 2 points collide? If the 2 points collide, right, in the symmetric product, so let me just take the 2 points colliding, maybe let me just draw it like this. If the 2 points collide, then in the symmetric product, you know, there's no confusion. You just call it 2 times the point, right? But in the Hilbert scheme, there is more structure, right? So for instance, if I have, so let's think about what we can do. So if you have kxy, right? So I guess we're doing C, so let me just go back to C, xy, right? Here is something that I can do is I can do x squared y minus ax, right? Something like this, right? If I look at this thing, right, the dimension of this vector space is 2. So if I look at something generated by x squared and y minus ax, which is supported at the origin, right? You don't get just one double point at the origin. The way you usually draw this thing is that you see, like, it's more data, right? You're at the origin, but you know, there's sort of a line, sort of a tangent direction with slope equal to a here, right? Maybe I should say y minus mx, right? So that you see that actually there isn't just one double point. There is a one parameter family of double points supported at the origin. So that if you look at this Hilbert chaomorphism, right? If you look at the Hilbert chaomorphism, you know, what it's doing, so if you look at what it's doing from x2 to x2, right? Then it actually is contracting the locus of non-reduced schemes. What that means is that what that means is that, you see, if you look at the locus of non-reduced schemes here, that's a divisor in the Hilbert scheme. So here it's a divisor. Now, how do we count this? You know, you have two-dimensional choices for the point, right? And then you have one-dimensional choice for the tangent direction. So you see, the locus of non-reduced schemes is three-dimensional, is in this four-dimensional Hilbert scheme. So it's a divisor, right? And then the image here, right, if I say that is just two-dimensional, right? So what it's doing is that it forgets what tangent direction you have here, and it just remembers that you have a double point, okay? As you see, the length of the scheme keeps getting higher, right? The structures that you can have get more and more interesting. So let's look at maybe when the length is 3, and then I promise I'll stop and I'll tell you the theorem and won't go one by one, you know. But so, you know, if you have 3 points, of course, what you could have is that you can have 3 distinct points, or just as we said, 2 of the points can collide and you have another point, and, you know, but, you know, the interesting thing is what happens if all 3 points collide, right? One way you can write something of length 3 is something like this. I keep doing K instead of C. So you can take CXY, right? Modulo, what you could do is you could do x cubed, and then you could do y minus a1x minus a2x squared, for instance, something like this, right? If I look at this, right, the dimension of this vector space is 3, so it gives you a point in the Hilbert scheme of 3 points on C2, the way I'm writing it, right? But, you know, this is the local picture. You can write this on any surface. Whoops. And the way you should think about this is that, you know, the way you should picture this is that you have something of length 3 here. You know, you have a little smooth curve, right? And you have sort of a length 3 scheme supported on that curve. But not all length 3 things are of this form, right? Like, you know, the nice thing about the scheme is that it's contained in the smooth curve, right? If you have A1, if A1 is not 0, right? You have y minus A1x minus A, I mean, even if A1 is 0, you have y minus A1x minus A2x squared. This is a smooth curve, right? So this length 3 scheme is contained in the smooth curve. Okay, not all schemes of length 3 have to be like this. So for instance, what you can see is that if you look at Cxy and quotient out by x squared xy y squared, right? This is the square of the maximal ideal. This also has dimension, is a 3-dimensional vector space. Again, gives you a point at the Hilbert scheme of 3 points. But now, of course, there is no smooth curve that contains this. The Zariski tangent space to this scheme is the whole scheme, right? The whole 2-dimensional vector space. So then it does not contain in any smooth curve. Okay. So this is to show you that. So this is the maximal ideal square. I don't know how to draw it. Maybe you draw it like this. Okay. All right. So this is to show you like the different kinds of schemes that you can get. And now you can imagine very easily that as the dimension, as the degree of the scheme increases, the possibilities get more and more complicated. But so this raises the question. So this raises the question of what does, like, so the question is, what happens if I look at schemes supported at the point? So the punctual Hilbert scheme. Punctual Hilbert scheme. Sometimes this thing is called the Birational scheme. And what this means is that this is, you know, schemes supported at a single point. Schemes of length n, or Hilbert polynomial n, supported at a single point. Okay, so for it's sometimes, as I said, it's denoted by Bn because of Briançon. And then the question that you can ask, what does this look like, right? In the case when n was 2, this was pretty easy. It looks like P1, right? Because, you know, I just choose a tangent. It's the projectivization of the tangent space at that point. But as you can see, already when you have 3 points, you know, you have curvilinear schemes, curves that lie on a smooth curve, schemes that lie on a smooth curve and those that don't lie on a smooth curve. So these kinds of things can get slightly more complicated. So what it turns out is that we understand this is a theorem of Briançon. That's why it's called the Briançon scheme, I think. So here is what happens. So let me tell you the picture. First, you have curvilinear schemes. Curvilinear schemes. And these are just the generalizations of the things that we solved. These kinds of this example, or in some sense, even this example, right, when n was 2, right? So we have the direct generalization of the n equals 2 and n equals 3 case. So that here what it looks like, you know, the ideal is generated by something like x to the n. And then what you do is you write y minus a1x minus a2x squared plus dot dot dot plus a, or minus, I don't know why I'm writing plus or minus, it doesn't matter what you write, of course, plus an minus 1 x to the n minus 1. Okay, now if you think about what this is, this really gives you a scheme of length n, because you see it's spanned, like this vector space is spanned by 1x all the way to xn minus 1. So the dimension, let me call this I, of cxy mod I is really n, right? It's spanned by 1x dot dot dot xn minus 1. If you have these things, then you can solve for y, right? Okay. All right, so these things are called curvilinear schemes simply because they lie on the smooth curve. So these are schemes that lie on the smooth curve. Right? And it's relatively easy to understand this, right? I mean, I can parameterize these guys by just giving you the coefficients a1, a2, all the way to an minus 1. So you see that this curvilinear schemes is really parameterized by an, affine n minus 1 space. Okay? But as I just told you already when we were thinking about the Hilbert scheme of 3 points, not all length 3 schemes are curvilinear. We have these schemes that, for instance, the maximal ideal square, that's not curvilinear. It doesn't lie on a smooth curve, okay? And here is Brianson's theorem. So Brianson says, again, we have a smooth surface, so X smooth projective smooth surface. Projective is not so important. Smooth surface, and then we look at the scheme Bn, right? And so this is, schemes of length n supported at a single point. So this is schemes of the space of schemes of length n supported at a single point. Okay? Now, what Brianson says is that this is irreducible of dimension n minus 1. And it contains this curvilinear schemes as a dense open subset. Contains the locus of curvilinear schemes as a dense open set. Okay? In other words, so let me sort of summarize what this means, okay? One conclusion of this whole story, right? The reason why I'm telling you is, one, I'm telling you the structure of the space a little bit. You see, in some sense, if you wanted to understand the Hilbert scheme, it's enough to understand these schemes Bn, right? Because, you can just look at the support of the scheme, and this thing splits as a disjoint union of these schemes Bn, where n is the the length, and then over the support of these of the scheme. So if you understood all these Bn's well, then you would understand the Hilbert scheme really well, right? But that's one reason. But the second reason is that, let's go back to the Hilbert chaomorphism. So let me remind you that the Hilbert chaomorphism was from the Hilbert scheme to the symmetric product, right? This is the Hilbert chaomorphism. And again, what does it do? What it does is it takes a scheme and it sends it to a support counted with multiplicity. And you see, what I said is that if you look, so here we have a locus, which I'll call B. So this is the locus of non-reduced schemes. Non-reduced schemes.
I think there is a question,
There's a question. Okay,
in chat.
Are there non-curvilinear schemes in Bn that we can write down and see as degeneration? Sure. I mean, like what this is saying is that, what this is saying is that every point in Bn is a degeneration of curvilinear schemes. So if you want to write non-curvilinear schemes, the easiest way to do it is write like monomial schemes, right? Like things with the form, you know, okay, so like if you want to generate non-curvilinear schemes, the easiest thing to do is write monomials of the form like, you know, x to the n, x to the n1, x to the n2, y to the m2, you know, y to the mj or something like this, things like this, right? So if you write things like this, you know, you're going to generate, you know, non-curvilinear schemes, assuming that, you know, you didn't make n1 or mj equal to 1. And then if you want, I mean, you know, at the end of the day, these things are even limits of things that are distinct points, right? Because it's irreducible. So like if you want to like explicitly see something like how is x squared, xy, y squared, the limit of 3 distinct points, for instance, right? You know, you can do it. So what you should do, I think, is like this. So take your A2, take your x and y axis. So take a point at 0 and take a point here like this, and a point there like this. What you can do is, I think, as, whoop, I can do that. If I don't recall, like, you know, if you just let this go like this and this go like this at the same rate, I think, then you will get x squared, xy, y squared. Answer to your questions, are they the limits of distinct points? Is yes, because we showed that they're irreducible. Okay, does that answer the question? Maybe. All right, so let me get back to what I was telling you. So here we have the Hilbert scheme, here we have the symmetric product and the Hilbert homomorphism, right? So we look at the locus of non-reduced schemes. So this is another way of thinking about this, is that we had the configuration space. This is the complement to the configuration space, right? So this is xn minus, if you want, the configuration space, right? So what this is saying, what Brianson's theorem is implying in particular, is that B is an irreducible divisor. Okay. So that will be an important thing for us to know. In other words, you know, the typical point of B looks like you have n minus 1 points, n minus 2 distinct points, and you have 1 double point, right? And everything is in the closure of that. You know, the way you show that this is irreducible is that you see that because of Brianson's theorem, there isn't just enough space to make, like, you know, you can't make too many of the points collide and get enough extra dimension to add more components to this, okay? So because you know these Brianson schemes are irreducible, then you can tell from there and that they're in the closure of these curvilinear schemes, you can tell that, you know, this B is irreducible divisor, okay? What was the point? Okay, all right. Okay, so now where are we going? So let me just tell you where we are headed. So the next what I want to describe is I want to start talking about the birational geometry. Geometry of Xn. I'll probably mostly stick to the case when X is P2 because it's easier to draw and, you know, it's fun. And then I don't need to tell you too much about surfaces and things like this. But so what does that mean? So, you know, the kinds of questions that we want to ask. So questions that we want to ask. The first question is, what are the embeddings? What are the embeddings of Xn into projective space? Right? Say that I want to understand the embeddings of this Hilbert scheme into projective space. So you see, what you do, there is sort of so in order to understand this, there is something called the ample cone. So now let me remind you what it means to be ample. So ample, so let me first tell you what very ample means. Very ample means that, so let's just take, so what is very ample? Suppose that you have a variety Y and you embed it into projector space. Okay, some projector space. Okay, then this projector space has a line bundle of one, right? Whose sections are the linear polynomials on projector space, right? All right, so then if you have this embedding, what you can do is you can pull this back and you get a line bundle L on Y, okay? Such a line bundle is called very ample. L is called very ample, okay? And in fact, you see, the converse of this thing is true as well. So you see, if you have a line bundle L over Y, right? Then you can look at the sections of this line bundle. So choose a basis for the sections of this line bundle. So this is a basis. Then you see you get a map, a priori only a rational map from Y to projector space, right? And what you do is you send the point Y in here to, you know, S naught of Y, dot, dot, dot, Sn of Y. Okay? And this is a morphism if, you know, the line bundle is base point free. If L is base point free, then this is a morphism, not just the rational map. Now, what does it mean that the line bundle is base point free? It means that these sections don't all simultaneously vanish at any point of Y. The problem is that you see, if all these points are zero, then you don't get a well-defined map to projector space. But if they're not all zero, then you get a well-defined map to projector space, right? So the condition for this rational map to be to be a morphism is that this line bundle is base point free. In other words, base point free, then you get a morphism, then L defines a morphism. And, you know, base point free just means that the sections of L do not all simultaneously vanish at any point of Y, okay? And if there is a point where all the sections vanish, you call such a point a base point of L, okay? So this is base point free. Okay, but just because you have a morphism doesn't mean that you have an embedding. So it's more conditions to guarantee that this is an embedding. And to say that this is an embedding, first, you know, you need to map distinct points to distinct points. And furthermore, you know, it's, you know, so you need to what's called separate points. And you need to separate tangent vectors. What it's not enough just to map, like, you know, here is an example, like I could take P1, right, and map it to a cuspidal curve, right? This is separates points, but, you know, at this point, it squishes the tangent direction. The derivative of the map vanishes. So it's not enough just to separate points. You also need to separate tangent vectors. What that means is that it needs to be an isomorphism on, you know, it needs to be a, it needs to be an isomorph, it needs to be an, it needs to map the tangent space injectively into the tangent space of projector space, right? Okay, but if you have those conditions, then you actually get an embedding, right? And, you know, so these two notions are basically the same way of thinking about, like, you know, thinking about very ample line bundles and embeddings are basically thinking about the same notion. And what is ample? Ample just means that, you see, it's very hard to work with very ampleness because, you know, it doesn't behave well under scaling and things like this, right? So what you do is you fix the problem by saying that L is ample if some tensor product is very ample. so that you don't deal with like, you know, these scaling issues and things like this, okay? In some sense, if you want to understand embeddings of Y in projector space, then you need to understand these ample line bundles, right? And you know, then of course you might need to understand also what multiple actually gives an embedding and things like this. But okay. But the first step is sort of understanding these ample line bundles. So as of question 1 prime, as you can understand, what is the ample cone of Xn? I'll tell you more about what this means next time. We'll talk more about like, what does it mean? Why is it a cone? What happens? Where is it a cone? And things like this, okay? So in a similar vein, you might want to understand the effective cone. So that's the second question. And this is the question, what are the effective divisors on Xn? What are the effective divisors? Okay. And then the third question that you can ask are, what other birational models does Xn have? I mean, here, you know, you can ask the question. So first we sort of looked at embeddings, but maybe I want to look at, you know, maps from Xn to projector space, but not this time, maybe not embeddings, but birational maps. The way you should think about this is that, okay, Xn gives you one compactification of configuration space. Are there other compactifications of configuration space that might be more suitable for, you know, other problems that you might encounter? Like, for example, if you want to understand the topology of Xn, you know, like, can you find some simpler spaces that lead to it? So maybe just to start out, right? let's sort of do the case of n equals 2, and then I'll stop there and continue tomorrow. So let's look at the case, the Hilbert scheme of 2 points, okay? All right, so we know some okay. Yeah, let me not do X, let me do P2. Let's just be more concrete. Let me take P2 and look at 2 points, okay? So let's be actually very concrete in that case. We can describe the space very concretely. So here what we did is that we took P2 cross P2, right? Then we went to the symmetric product, right? This is mod by, this is quotienting out by the symmetric group, right? Here we have the Hilbert Schemes morphism. Now, you see, here is the way to think about it. Is here in P22, there is a P2 parameterizing the diagonal points. P2 parameterizing the diagonal points. Or if you want, here there is the diagonal. This is the image of the diagonal, right? Now, what the Hilbert Schemes morphism does is that it blows this up. Or there is another way of seeing this Hilbert scheme. And this works in general, not just for surfaces. It works for any dimensional variety. Here what you could do is you could take P2 cross P2 and blow up this diagonal. And then you can quotient up by the S2 action, okay? It turns out that, you know, in this way, you can understand the geometry of P22. And I mean, actually, I didn't have to specialize this to P2. I could have just done any X, but let's look at P2. And then you see this P22 has one more map. So one interesting map, of course, is the Hilbert Schemes morphism. So this is the symmetric product, but this also maps to if you want P2 dual. Now, how do you map to P2 dual? Here is what you can do. So if you have P2, right? And if you have 2 points, then there's a unique line spanned by those 2 points, right? And the lines, and so, you know, given 2 points, I can just map the 2 points to the line spanned by them. So that gives me a map to P2 dual. A priori, it's only a rational map because you have to worry what happens in case the points collide, right? You see, so you don't have a map to P2 dual from the symmetric product, right? Because if the points collide, then there isn't a well-defined line associated to it. But in the Hilbert scheme, there is a well-defined map associated to it because, you know, like any scheme of length 2 is contained in a unique line. Because remember, the equation of such a thing still looks like, you know, x and y minus mx, right? So it's x squared and y minus mx, right? So there is still a unique line that contains this, so that you actually get a map to P2 dual. So that you see that, you know, the kind of game that we want to understand is we want to understand maps from the Hilbert scheme, right, into various other spaces that will help us understand the topology of this. So for instance, you know, in this case, you know, I can view P2 Hilbert scheme of 2 points in P2 either as a P2 bundle over P2 dual, right? So, you know, I can view this thing as a projective bundle of P2 dual or the blow up of the symmetric product. Each of these things tell me something about the geometry of the space, and then the game is going to be, how do you understand these maps? How does it allow us to tell what the ample cone and the effective cone are, and things like this. So that will be the subject of the next 2-3 lectures. Okay, so maybe I'll stop here and see whether there are any questions. So, you know, this was a relatively quick introduction to the Hilbert. You know, you can Google and find lots of more leisurely introductions, but hopefully I drew enough pictures that you see the picture of what these things look like a little bit.
Oh, okay. I think there is some question in the chat.
Is there a combinatorial way of studying Hilbert schemes? For I had the Newton pulley in my way, it looks like not enough. Okay, so so the question is like, can we study things combinatorially? Yes, especially if you're looking at P2 or something like this, or A2, right? One way that you can study the Hilbert scheme is that, so you see, if you have P2, then there is a torus, or even A2 if you want. I mean, it doesn't matter. Let's say that A2, then there is a torus action. Torus action on A2, right? And then, you know, so what do you know? So you go TX, inverse Y, or something like this. Something like this. Yeah, you know, is that what I want to do here? I think. Yeah, so you know, if you look at that, this kind of torus action, then you can look at the fixed points of the torus. Oh, because you have this torus action on A2, the torus also acts on A2N. Okay, and then you see the fixed points of the torus action. You can describe these are the monomial ideals. All right, so these are things that are, you know, given by things like this. I did this xn1, xn2, yn2, ... maybe ynj, right? I mean, the way you denote these things is you denote them by box diagrams like this. Something like this, yeah? Okay, so these are the combinatorial objects associated to these monomial ideals. You can write down the resolution and things like this in terms of this, right? And, you know, then you can decompose the Hilbert scheme, you know, into cells. So the Hilbert scheme decomposes into cells. This usually goes under the name of Bielanitsky-Birula decomposition. And then, you know, you can study the geometry by, like, you know, in terms of these combinatorial objects. If you want some notes on this, I think Diane McLagan had some nice notes on the Hilbert scheme, some lectures she gave. If you Google them, then you can see some, you know, some explicit combinatorial descriptions of some of these Hilbert schemes. Yeah, these were the original ways that people computed the Betty numbers and stuff like this. Is some of these P2N and A2N originally. The work of Ellensrud and Strom and some of you know, the early work. So let's see, there is another question.
Yes.
How to understand the Hilbert-Chow morphism as resolution of singularities of X and is not smooth. So the Hilbert-Chow morphism is a resolution of singularities only when, you know, really only when we're talking about the surface. In general, the Hilbert scheme is not smooth. You know, I mean, if you look at even the Hilbert scheme of 4 points on C3, yeah, this is not smooth. So it turns out that if you take 3 points or 2 points, it's always smooth. And, you know, 2 points, you know, I just did this diagram just for P2 here, but you could replace it for any X. If you want to understand the Hilbert scheme of 2 points, and here, this is any dimensional thing, right? Then you can view this as the blow up of the diagonal. Blow up of the diagonal in the symmetric product. So it is a resolution of singularities in that case, and it's smooth. But, you know, in general, the moment you have even 4 points in a higher dimensional variety, then it's not smooth. And the point where it's not smooth is that you can take the maximal ideal given by x, y, z, right? And you take m squared given by x squared, x, y squared, x, z, y, z, z squared. So if you look at a point like this, then the Hilbert scheme is not smooth. If you want to see this, so the dimension of C34 is 12. The tangent space at the point like this, I forget, this 18 or something like this. So let's see what it looks like. So you see, so I is generated by, let's compute the dimension of tangent space. We have x squared, xy, y squared, xz, yz, z squared, right? So I need to give you a homomorphism from I to O mod I, right? So you know, a graded ring homomorphism, a graded kxyz homomorphism from this thing to this thing, right? So what does that mean? I need to tell you why x squared needs to go to, you know, a1 plus a2x plus a3y plus a4z, you know, then xy has to go to b1 plus b2x, things like this, and, you know, z squared has to go to similarly. So we have 6 of these things, a, b, c, d, e, f. So that's f1 plus f2x plus f4z, right? So I need to tell you which, like, you know, I need to give you an XYZ homomorphism, a CXYZ homomorphism from this module to this module, and it's graded module homomorphism, right? So one thing that you notice that, you know, if wherever x squared goes, if I multiply this guy by y, so let's call this map F. So let me just write it like this. So that's more like math rather than babbling. So, you know, x times fy squared, y times fx squared had better be x times fxy, right? You see, if I multiply these things by x or y or whatever, then they lie in the ideal, so they become 0 except for the constant terms, right? So that you see that if this is going to be consistent, right, some constant times x has to equal some constant times y or whatever. So that's not going to happen unless all these constants are 0. But that's the only requirement, right? So these guys have to be 0. That's the only requirement, so that you see that this is an 18-dimensional space, right? So that you see that that point is the Zariski tangent space at the maximal ideal square is much larger dimensional than this 12-dimensional thing. Okay?
There are two questions.
Okay, then another question.
Yeah.
Oh, the morphism is defined in any dimension. The Hilbert-Schemes morphism exists in any dimension, that's correct, but it's the resolution of singularities only when the dimension is 2. And it's an isomorphism when the dimension is 1, so I suppose in that case. So then one more question. Any guess what is the smallest n for which C3n is reducible? No. So, you know, I told you that xn is reducible if n is sufficiently large and the dimension of x is at least 3, right? So we know exactly, so here, if the dimension of x is greater than or equal to 4, then xn is reducible if and only if n is greater than or equal to 8. Okay? We know exactly, if the dimension is at least 4, we know exactly when these xn's are reducible and irreducible, okay? If you have few points, they are irreducible, and the moment they have enough points, they become reducible. And if the dimension is at least 4, enough points means n equals 8, okay? And this is sharp, like it's an if and only if. If the dimension of x is equal to 3, then there are various theorems here. You know, these numbers change. I think that xn is reducible. I mean, what I proved for you is that if n is 9 to 6, this is Yarabino. I think these days, I want to say this known maybe for roughly 78 or something like that. I mean, you know, these numbers change and I don't quite remember what the actual number was. And then, you know, it's known that it's irreducible, again, something for like n less than 12 or 13 or something. I mean, I don't, these numbers again change. People prove more and more things. So, but you know, there is a gap here of, you know, 50, 60 that we don't know what happens.
So,
I mean, yes, sorry.
No, just go ahead. Go ahead, please.
The other question that you can ask, I mean, you know, like, you know, we don't understand the dimensions and the number of irreducible components, like the dimension of x and the number of irreducible components. These are all open problems. We don't even know whether like there exists a non-reduced component. Again, for these questions to make sense, my dimension is at least 3. So we don't know how many components you have, what are their dimensions, and we don't know whether they're non-reduced components and things like this. So, you know, there's this one of the things with the Hilbert scheme is that, you know, various Hilbert schemes satisfies what's called the Murphy's law, which means that whatever horrible property you can imagine that occurs in some component of the Hilbert scheme, the way to make that precise is maybe like whatever singularity that you can write, you know, with integer polynomials occurs in some component of the Hilbert scheme. We don't know whether that kind of property holds for Hilbert schemes of points and higher dimensional varieties. I mean, these kinds of things are interesting questions that we don't know. And there are bounds, of course, like, you know, there are regularity bounds and things like this that bound the number of irreducible components. You know, you can use this kind of Arabino construction that I gave you to construct many components. So like, you know, in some sense, the number of components grows exponentially, but we don't know, like, as n increases, but we don't really know how many there are and what are their dimensions, what they all look like. I don't know, did I answer most of the questions on the chat?
Yeah, there is no question anymore.
All right.
So is there any question more or comments? I think no. Thanks for lecture.
Sure. So, all right, I guess we'll take up again tomorrow.
Yeah.
Discuss more about the birational geometry.
Yeah, we are going to start lecture tomorrow, 10:30 with Özgür Kelek, Can Bahadır, 2:30, and then 4:30, İzzet Coşkun will continue his lecture. And today is all, and hope to see you tomorrow.
Thank you very much for nice lecture.
All right, thank you.